Okay, so it's around 2:30. I think I'm gonna just get started on time. People might come in late, but it's fine. Because I'm starting with a really fluffy thing, which is my title image for this presentation is a painting by the Italian Baroque master Caravaggio. I wanted to kind of instill some culture in this group of programmers, and it's Narcissus, who is the figure from Greek mythology who stared in his own reflection for so long that he turned into a flower because he was going to die. But this might be a more accurate painting from a more modern era, and this may look like some code bases you've worked in. If it does, I feel sorry for you. So if you're in the audience for this talk, you probably have some idea already of what reflection is. But because terms are very overloaded in mathematics and computer science, it's always good to define our terms. But another philosophy I like to follow is when you're trying to design a solution to a problem, you should really start with the problem rather than coming up with, some mechanism you think is cool. And I mean, that's fun too, but if you're going to change a language, it should be motivated by a real use case. So this is one problem, one example is, this is very common. You have some graphical library, you're trying to draw shapes. And you have some primitive shapes, boxes, circles, maybe you have some more primitives defined by a rendering library. And then you have some more types that are defined by composites of shapes. And you want to define a generic draw function that takes some information about a shape and renders it by composing these primitive functions. One solution to do this is you could make a composite shape where you have a vector of boxes and circles and your other primitives, and then the draw function is very simple to write. You can iterate over these vectors. You could also do this with inheritance. I'm actually not showing that because it's a very common example. And there's another, one disadvantage of this approach is you're losing information in the type system when you have this composite shape approach. If you wanted to distinguish many different kinds of shapes and make more distinctions between them at compile time, there's no way to do that. The values are only defined at runtime. So, the converse approach of that is, suppose I define different structs that are composed of my primitives in a certain layout. So for example, a capsule or a pill is defined by a box in the middle and two circles at the ends. And you can hand code your draw function by drawing the circles and drawing the middle. But this is extremely tedious to write to just, recursively essentially invoke this draw function for all of the information. Imagine writing this for hundreds of objects in a huge code base, and then imagine maintaining that. Imagine trying to add a new primitive shape and then backport old shapes. So it seems like maybe there's a mechanism we're missing. So how about an API that could take the members of a given type, a generic type, from which we could derive this generic function where we could look at if the members of our type conform to a certain concept at compile time, and then if the draw function was defined, which we determined by some compile time predicate, invoke the draw function and render our primitive shape. I'm going to call this introspection. And I'm going to explore what introspection is, what different solutions there are in the language today, and what the future proposed solutions for maybe C++20, maybe C++23 will look like. First, I'll start with existing solutions. You could have, some people call IDL, interface description language, or schema-based code generation. You could actually use a compiler or a C++ parser to generate reflection information. You could have a macro, no external tooling, just using the preprocessor. Or you could use some crazy new stuff. And the particular example I'm going to show uses C++17. It's a particular library by Anthony Pelukin. So one example of this first technique is CapMProto or protobuf. It's not really providing introspection, but there is CapMProto actually has a runtime introspection interface where you can define a struct. This top part is not C++, it's their schema definition, where you specify a struct using their schema, and then it generates C++ code. It says, I have a member named name, and then I'm going to generate a function called getName. And because all the code generated using Cat and Proto conforms to this interface, they have a very efficient serialization library that can serialize and deserialize things defined with a struct. But that's very brittle because you need to go through their external schema process in order to use Cat and Proto to serialize anything. So again, they have a generic runtime reflection interface, which I'm not showing here, but it's a way of, instead of directly using these concrete getName, getAge, which are generated, they basically type erase structs that are defined through Cat and Proto. So the next technique, which is more interesting, I think, for C++ people, is what if you could use a parser? This is also what Qt mock, the meta object compiler, does, but I don't think it uses libclang. I think it uses their custom parser. And they also, a lot of differences from what I'm showing. This is from C++, a reflection engine by Manu Sanchez, where he takes C++ code, structs, parses it with libclang, and then uses a kind of combination of Python and some templates to then generate compile time structs that only have these meta information, no runtime values. And then that is used as a basis for a static reflection library. So the disadvantage with this is it's not portable, and it does require some external tooling. Well, not portable is not accurate, but it essentially forces you to use libclang, and that, for example, might not be available on Windows yet, or might not be reliable on Windows yet. So moving on. Also, if you have questions at any point, this goes without saying, but please, just hands up at any point. So, let's say we're sick of all this external tooling stuff. We don't want to add a separate build step. We just want to be able to reflect on our members in C++ code. So you can use a macro. There's an implementation in Boost Fusion, in Boost HANA. There's a person in this room who wrote a serialization engine called Iguana, who wrote his own reflection macro, where if you pass the types and the names of members of a struct to this macro, it will adapt them to be used in kind of this reflection interface with tuple-like access. So this is one way of defining a struct to be used with reflection using define struct. Or if person, the struct we're trying to reflect on, is not defined in your header, you can also adapt it externally. But the caveat is you have to know the types and the members, and you have to pass it to the macro. So this is an example of how you'd use the result of this definition. You could write using this heterogeneous for each, you can write a generic print function where we can print the name of the field and the value stored in that struct. So this is a very brief overview of how it works. Actually, embarrassingly, the author of the macro I just showed is in the room, so if anything's wrong here, he can correct me. You take a look at the macro. You look at the name of the member, and you can stringize that to be used. So that's how we can convert the name of the member into a const ** to print it. You can also use that identifier name to get the member pointer, and that's how we're going to set something using the. I didn't show setting, but the set or get something from the struct, and then you associate the name and the member pointer in pairs, a tuple of pairs, and then you specialize a lot of templates, and you basically the implementation of this macro requires for a max if it requires n specializations for some large number of n, and that's the maximum number of members you can reflect on. and it's actually generated from a Ruby script that generates a C++ macro, and that macro is generating code for you when you write C++. So it's a little bit of a monster. Another really interesting library in this tradition is really cool because it doesn't require you to know and to enumerate the members of the struct you're trying to reflect on. So this it used to be called magic get. I think it's now called PFR. What I want to call attention to is this PFR flat get of I, where I is a compile time, or it's a non-type template parameter integer. And basically, your members will get ordered 0 through n. And you can use a compile time integer to access your members without any of this annotation stuff. And the caveat is it only works on pod types, plain old data types. You can't even use standard string. You have to use a const char star here to represent the strings in our person struct. So this is a similar, like, this isn't using HANA, so I decided to write my own recursive for each kind of or print function for this, but tell you to achieve something similar. Another disadvantage is we don't have the names of the members here, unlike in the HANA example. And so how does it work? Well, it's kind of cool. You can actually, the C++ 17 version of this library doesn't use any macros. No use of the preprocessor, so that sounds really great, right? Like the preprocessor is terrible, and we should get away from it. Well, I don't know about that. The way it's implemented is it uses structured bindings to destructure a tuple. This make tuple of references is doing some kind of crazy stuff with reinterpret casting your struct as a tuple and then destructuring the members. And again, this is overloading essentially. Yeah, it's overloading based on the second function argument from 0 to 100. And so you see there's A, B, C, D, E, F, G is are the dummy variables he's giving to destructuring. So is this better than a macro? Nah, I don't know. So clearly C++ has some catching up to do, I think, because other languages have reflection facilities. And I wrote a couple of blog posts on this, or 2 blog posts on this subject, and I go into a little more depth in those blog posts. And you can Google also for how other languages do reflection. And I think all these examples, Python, Java, and C#, they all offer fairly powerful reflection interfaces, but it's essentially all runtime. I mean, in Python, it's a dynamically typed language. All of their structs are essentially dictionaries, so you can do some really powerful stuff with that, but it's at the cost of performance. Another really interesting thing about C# that I learned basically this week is that you can kind of arbitrarily compile C# code at runtime and then use those types. I think Peter is in this room. He knows more about that. I don't know, you wanna? Anyway, but another thing I learned just this week, so I added a slide at the last minute, is dlang, which we'll hear a keynote about tomorrow. They have some really interesting compile time facilities for the kind of thing that I want to do in C++. First of all, they have that underscore traits. I don't technically know what interface. Where you can get all the members of a struct, you can get all the overloads of a function, a lot of other stuff. You can get the name as a const expr string, and they even have this thing called compiles, where for a given expression you can just check to see if that will compile, which is quite powerful. And they have this thing called mixin, which is I think technically what you'd call a hygienic macro, but excuse me, you can define a const char array, and I believe in D that's going to be what we think of as const expert by default. You can write a struct, and then when you call mixin of that result, then that is essentially compiled at compile time. And so this, I apologize if you're not familiar with the syntax. I'm also just getting used to it. This is like some of the first D code I compiled. You can pass a const expr string to this definition of defining a struct template, and then just create a foo with a bar member. I think this is pretty cool. Okay, so again, yes, Louis.
This is a little bit like this is not too far from the explored code injection mechanism, right?
Yeah. So the comment was, this is not too far from the explored code injection method. And I guess you're referring to the design space for reflection. Yeah. It's very, very flexible. And I think the biggest complaint is this, because you're writing code, like concatenating tokens, it's crude. People want kind of more enforcement of an interface through an API, like an EDSL or something. We're going to get to that at the end of this talk. So, as we just mentioned, there's some proposed solutions in C++ for this. I'm going to focus on two today. The first one that came along, or not the first reflection implementation that came along, but the older of the two I'm going to talk about, I call reflexper. It's based on a paper by Choklik. I'm probably horribly mangling his name. I'm sorry, Matus, if you're watching this. And Axel Neumann. They also co-wrote another paper. They were joined by David Senkel, who's in this room. Hi. Called Static Reflection in a Nutshell, which explains the design rationale for their API, proposed API. And what was really fun for me is they have an implementation in Clang, which was primarily by Matus, and decent documentation. This is a very, very simple example of what it looks like. You use the reflexper keyword on a type, and that returns another type, which is a templated type that carries the information about the struct. And then you use a series of meta functions such as getBaseName, which gets the name of the struct as a const char array. GetSize returns the number of members, and I'll introduce more as we see them in code examples. So the other reflection implementation I'll sometimes call operator $, or CPP3K, because that's the name of the utility header for this API. So it was released after the original reflexper paper by Andrew Sutton and Herb Sutter. They also have a reference implementation in Clang. The $sign is a little bit controversial because it's compilers disagree about whether or not that's a valid identifier. But for me, that's just a bike shed issue. I don't care about that much. I care more about what the power of the API is. How can we measure that? What will this allow me to do? And also, what does it look like? Is it expressive? Is it something I'd like to use? Okay, the $sign is one part of that because it's just one character, but some people complain it looks like Perl. This is what using it looks like, which I consider more important. And you use the $sign to reflect on a type, and that gives you a constexpr value back. And you query that using value semantics. So you can use metainfo.name to get the array as a const char star. You can do .member variables, and that gives you this sequence. It's not a tuple, it's something different. And then you can query the size of that. Which API is better? Well, this is a question. I think this is a bit of a misleading question. But I do want to do a little bit of comparisons using examples. And I want this to be an example-driven talk to kind of ground us in reality. One note is the static reflection in a nutshell paper does say maybe we want to provide a really basic API, and we do expect people to build some metaprogramming facilities on top of that, depending on their use case and also what semantics they prefer. I think that's a point of discussion. But one example of what you can do with reflection is you can create a generic equality operator for a given type, or determine if it's impossible to create such a thing. So I'm going to refer to record types. And when I refer to a record type, I mean something that has members, roughly. It may have a more technical, pedantic definition. But if I want to, I have a type T, and I have a TA and a TB, and I want to determine if they are if they're equal values, not if they're the same, not if they point to the same address in memory, but if they're record types and all of their sub members compare to be equal. So suppose I have concepts, maybe, or some compiled predicate that says T is equality comparable. It has a valid, and for this purpose, it has a valid equal. I will return A equals B. If it's iterable, maybe I can do something where I have a data structure where I can go through every member and compare if those are equal. Obviously, if they're a different size, like if this is a vector, it can't be equal, so we return false. Okay, but, and this is, kind of these like heuristics for how we compare a T. But what if T is a record type and we don't immediately know how to equality compare them? We can get all of the members of the T using reflection, get data members from the result of reflex per T. And then for each of our data members, we have to access the value and then recursively call equal to get the result of the submembers if those are equal. So this meta for each that I'm using is another facility provided by the reflexper utilities, which is a function that takes a lambda, and in the angle brackets, you give it the sequence that you want to iterate over. Another important thing we'll keep seeing over and over again is the way we do accesses with the fork right now is we have to get the member pointer out of the using the meta information, which is like a little bit scary looking, probably for like novices. Some people in the room are like shaking their head being like, what is this? So comparing, this is what the other fork of Clang looks like. It's shorter. They also have a meta for each. Rather than taking a sequence in the angle brackets, it's the first argument, the t.member variables. And it's similar. So, okay, you may have some observations, complaints, whatever. I'll predict them here. Comparing them, you might say, hey, I really like the second implementation a lot better. It's shorter and it looks a little more natural. Okay, sure. What I really don't like about this example is that the for each is potentially very inefficient. And also maybe hard to use, like logically difficult, because it requires an initial valid state, or basically an identity for our operation. Luckily, with equality, we have that because the identity for and is 1 or true. But another problematic thing is the for each construct doesn't allow us to early return or short circuit, which we can. Yes.
Technically, you can do it by throwing an exception.
Thank you. Great point. And another thing that may concern you is what about public versus private? I didn't see any of those words on that slide, and how should those be considered in this comparison operator? Okay, so I want to address the second point first. I think fold expressions are a really nice way to solve that problem. So this is, I had a lightning talk about folding expressions yesterday where I gushed about them, and but the thing with fold expressions is you need to have a parameter pack in order to fold over that. The reflexper fork does provide this thing called unpack sequence, or an unpack sequence : type or _t. And that says if you have a struct that takes a pack, a ... variadic template arguments, and if you pass get data members to that pack, that will unpack it as a sequence. But if you don't use that, this get data members cannot be understood as a parameter pack on itself. So it's like a little annoying to use. But it does allow us to write this nice fold expression where we don't have the initial state problem anymore because the fold expression will just take the first result of the operation. And the compiler can optimize this better than if we go through the meta for each. Because the fold expression is basically expanding these different results, and it has and in between them. So the and could be short-circuited by the compiler. I apologize. I didn't take benchmarks for this assertion, so I could be wrong, but I think it could work. Okay, so the next thing I want to address is this access specifiers discussion. So in the current state of the implementation that I worked with, understand that with the proposals, things are always changing, is by default, get data members and the member variables in the other implementation reflects on all public members. In the reflexper implementation, there's a get public data members, which will only give you the public data members. And both of the implementations provide an is public or an is private for a meta information. So at compile time, you can determine if a certain member is public or private. So if you have something that gives you all the data members, you can then switch on the if this is private, then don't do anything with it. So as you can imagine, bypassing private is really, really easy with this implementation. So actually, I'm going to say easier because in the language as it is today, you can bypass private using some crazy stuff. And there's a blog post. You can Google bypassing private in C++ to find it. But this is like way easier because when you use meta information to get when you get data members, you can get an element using a compile time index, and then you can get a member pointer from that. And this will actually compile, and it actually won't reach this assertion. So I'm able to take the private member X out of A and copy it into Y in B in the constructor of B. So this may give you the heebie-jeebies, or maybe not. I don't know. Yes, Alistair?
I say accessing private members is not really scary because you're not violating any invariants of the class. Modifying private members might be scarier.
Right.
And all your examples so far are pulling, so
Exactly.
it's not scary. Yet.
David?
So I can give some kind of motivation for why we're doing this. It's because they wanted to make sure that if you only use get public members, then you know the code is safe. So it's very easy to grep for that. And then there's something that's been added on top of this, which is get all the members based on what kind of scope you're in. If you're in a scope where you can get private members, then you can get those. But there's still get all members if you want.
So, yeah, my general feeling is I think if we get reflection soon, the guideline is going to be you should reflect on public member data by default and continue the guideline with access specifiers we already have, which is use private members for implementation details. That way, if you are serializing something, for example, you're going to avoid having kind of like compatibility issues between serialization formats. I do think it's very uncommon, actually, to have the what I showed on this slide, which is I'm using 0 or a compile time index to directly grab a member pointer, but you can do it. So it does seem like in order to follow the rule that arbitrarily modifying private members from any scope is not a good feature of the language, then I think it seems like the wording in the standard should be made careful for that. And I also think the get public data members convenience accessor is like very important for that reason. Yes?
I have a question about, well, since you mentioned serialization, is there any way for us, in either of these proposals, to specify a subset to iterate over, say only the serializable members, and I can myself annotate which ones should fall in that set and shouldn't fall in that set?
I'm going to actually show a code example with serialization.
Okay.
I don't do exactly that, but I'll try to point out where you can switch on that. Yeah. That's funny.
So the way that we're doing the proposals, we're trying to do the minimal subset.
Yeah.
And then
There was
later on we'll do.
Yeah. I'm asking about the discussion. I don't remember the exact how the discussion on the code is.
There hasn't been a proposal for attributes yet.
Yeah, since, sorry, I don't know your name, in the audience mentioned this, it's very timely. My next example will be, how do we do serialization and deserialization? Actually, so Louis at Meeting C++ 2016 in his keynote showed like a one-slide JSON serializer example using value semantics, metaprogramming on top of reflexper. At the time, the other fork hadn't, or the other proposal hadn't even come out yet. I'm going to show deserialization today, since, JSON serialization with reflection, that's already been done. this is actually going to have a lot of overlap with Matt Calabrese's talk from earlier today. So if you saw that, I apologize. Oh, there'll be some other stuff too. And again, a lot of the string parsing and the API itself this is a bit of a toy example. So if you see like, oh, you're not perfect forwarding here, like it's okay. Like, I mean, feel free to point it out. But I more want to point out how I think what common patterns I think we're going to need if we get reflection. So the interesting thing here is, I guess I'm not gonna. I deleted a slide where it would be a good time to answer your question. So the way this deserialized function works is it's similar to the equality. Serialization is very similar to the equality example. You are looking at a struct and you if const expr over some concepts, compile time predicate about the struct. You can say like, if I'm serializing into JSON, if it's a string, I can just write name of my member, the string. If it's an int, I know how to convert an int to a string. Easy. Then in that kind of compile time switch, you could say, if this is not a type, if I know this is not serializable, I'm just going to skip it. And then what I do in this example is if this is a record member, if it has members, I'm going to use reflection. And that is when we use reflection to look at the members of the record and then recursively call serialize or deserialize. So in this case, when we have deserialize, we can't just use compile time information about the struct because we have this input that's determined at runtime. So imagine, I probably should have written some JSON on the slide, but imagine you have a key that refers to the name of a member. How do you know what field in the struct to map the corresponding value to? Well, you have to map a runtime value to a compile time value. And this is a pattern that's kind of the backbone of variant visitation. And if you're in Matt's talk, we kind of implemented that using his library. I'm going to also talk about that today. So one really naive way of doing this is, okay, imagine you have, for one level of your JSON object, you have all the keys, all the JSON keys, and then you have the strings representing the values for those keys. And you also have a T that has member variables. I'm going to take my key and my value, and I'm going to say for each of my member variables, if the key matches the name of the member variable, which we know through reflection, which is a compile time value, but I can compare a runtime value to a compile time value, then deserialize it. And we, again, use access using the member pointer. So this might seem... Yes, Jeff?
So quick question, the deserialize, is that a user-written function, or where does that come from exactly? Is that something you're going to generate?
Yeah, deserialize is something I'm writing, and I'm recursively calling it. If we have time at the end, I'll show you guys the full example. I omitted a lot of the code to show the highlights, but
I guess the reason I'm bringing it up is because you can imagine for a moment that your in-memory representation is an integer value and your external representation is a string. And so it's not as simple as it might seem to just serialize and deserialize to the same type.
So the comment is your in-memory representation might be an integer, your value is a string.
Right. So it's a date, 2000.
Yeah.
And internally it's an integer.
Yeah. So I think in order to handle that, you would have to have a customization point for deserialize that says this type in my struct is a date. And then the overload for deserialize for date does something with that string that's completely different. Yeah, I don't get to that because I think that's kind of more of a deserialization. This is not a talk on deserialization. This is a talk on reflection. So sorry, that's kind of a defer. But
No, but
yeah.
But I guess what I'm saying is I think obviously I can see where reflection would really help serialization, but there's got to be these customization points because otherwise you won't be able to do it.
It's a common counterargument because some people are like, I really need reflection for serialization. It's amazing. And other people have that same example where they're like, well, I have so many special cases for my types for serialization that it doesn't matter. Like, I can't just auto-deduce that. I think it depends on a lot of factors. Like, it depends on the kind of code base you're working in. My motivation was, I was working in robotics, working on this framework where we had message types for a lot of mathematical types, a lot of like kind of custom messages, the kind of thing people use JSON on the web for, like control things. So then there was like a lot of repetition. I think at almost any case where you're using a code generator, like the first example with Captain Proto, you have a code generator and a schema specification, and that's just generating code blindly for serialization. You could just use reflection instead. Yes?
On this topic, I mean, the way that they do this in C# is that they reflect your entire data structure, but if any of your members implement this
Yep.
serialization protocol, then it'll just quickly call that rather than do the default. So
Yeah.
that's all that problem.
The comment was in C#, they use reflection, but they also use like serialization traits as a customization point, essentially. Yeah. Cool. Okay, I'm going to move on a bit. As I said, this is kind of the same pattern of this recursive call over all the members. That's quite simple once you understand the syntax, I think. And then the string matching, for me, I wrote this and I was like, this is going to be like really bad runtime performance. Usually when we do metaprogramming, it's like, okay, this might take a really long time to compile, but I know that I'm pushing some cost from compile time to runtime. But this is basically O of n string comparisons per member in the struct. Okay, hold that thought. I want to, yes, Alistair.
But in these cases, n is typically going to be tiny,
Right.
so we're probably not going to be too concerned.
Yeah, like, okay, what's the average number of members in a struct? 15? 4? Another question is like, for an aggregate type, like not just one level of a struct, but like, you know, you have a struct that has many subcomponents. Is that more like, yeah, okay. I'd love to see some data on that if the like larger companies like Bloomberg or Google have collected data on that. So I wanted to do another practical example to ground us in reality again, and that's program options. Really common problem is parsing argc and argv. Like almost every program does this, right? So what if we wrote this cool library where we could write a struct called program options, and it's maybe a pretty simple flat struct that defines members with names of things that map directly to their argument flags on the command line. So for example, standard string file name, you'd specify setting that in program options as -- file name or -f. And the interface to our toy library is just parse argc argv, and it's going to return an optional that is null-opt if we found an invalid flag or if there was something weird about the argument vector. So the way we're going to do this is we're going to use Hana basically for the compile time map. And we're going to reflect on the program options struct, look at the name of the member, and make a flag, collect the flags out of that, then map that to the meta info from reflection that we get in a map. And just as a really simple example, we're going to select the next character if we find kind of a collision in the map, if the short flag has already been taken. And if we can't do that, for now, we're just saying, I couldn't think of a clever way to arrange your flags, so static assert. If I were to spend more time on this and have people actually use it, there should be a way to add a customization point for custom flags, of course, and also for help. But this is the kind of the bare bones of super minimal program options. At runtime, the parse function is going to iterate over argv. We're going to do the same thing we did before, where we have to convert a runtime determined string, in this case it's a C-style string, into a constexpr string to index into the map to get the information about how to set the thing in the program, the value in the program options struct. This is the basic kind of a part of the implementation using the reflexpr API. I haven't pictured this collect flags lambda, which is doing exactly what I just said. And this is what it looks like using the other fork, where I had to write, this is kind of annoying in the state of the code right now, is I had to write my own function to adapt their tuple representation to HANA. And I also couldn't use std_apply because they don't use standard tuple. This is a bit of a nitpick, but it's like I'd like to see a consistent set of data structures that play well with each other. If you have some questions about that, or if you have ideas about like the design for this, then let me know, or let the people writing the papers know. One of the things that I want to point out from these slides that came up is this collect flags lambda in the fold expression to HANA is kind of annoying because we have to deal with constexpr strings, and there is not a standard way to deal with those yet. In fact, the common syntactic sugar to make them nicer, which is using a user-defined literal, is like not even for user-defined literal of character pack. It's like not even a standard compiler thing. It's a GNU compiler extension, so that's great. There's also in the different forks there's different representations right now. So in reflexpr they decided on const char array of size. So n is determined at compile time, and I don't remember if you can actually grab that from the like get base name length. The $t.name is a const char star. It's kind of annoying is because you can't pass these into functions because you can't have constexpr function parameters. And also, this is more just an implementation detail, but the HANA map that I'm using, I couldn't get this to work, but like the keys have to be HANA strings. They didn't work with a different, like just a const char star or a const char, yeah.
So that's because if you compare const char stars, well, first of all, you're comparing
values.
So that's what you want, but also
Yeah.
it's going to return a bool, and not an integral constant bool.
Yep.
That's the whole story with constant parameters, so that's why it is.
Yep. Yes, David.
I would just point out that the latest version of the paper, we're returning not a const char n anymore. We're doing a, what was that thing you just said? Numeric constant of like char pointer or something like that. We're doing something crazy, but it's just there.
Well, if you had
there as a stand-in for getting real compile time strings. So
if you had an integral constant of a const char star, that still wouldn't help.
yeah, that will.
That will?
Yeah,
Oh.
Yeah. If you
Oh my
find
God.
a comparison. If they're not terminated, it's gonna work. Yeah.
Mm.
It's crazy.
So it has because you can implement like a constexpr strlen using that.
But you just do constexpr count, right? And,
Yep.
and that's it. But by default, your equal, which Hannah's gonna use, is gonna get the pointers. So you're gonna have to change that.
Wait, but if you were class that right now, couldn't take class char star as
I don't know.
a value? That's the whole issue around.
No, I think it can. But this is.
No, it has to
I think we should take this.
Okay, we'll talk about constexpr strings later. I have a I didn't have access to good facilities for dealing with compile time strings, and I was too lazy to write them myself. So I have essentially a stopgap solution for dealing with these, which is unpacking the result of the reflection name and doing some crazy stuff with index sequences and then putting it in a HANA string and then just not dealing with the strings afterward. If I had a library with an API where constexpr strings were like something that the user of the library had to deal with, I feel like there's a solution that's not in the standard library right now, and that's there's something missing. There are facilities that are missing. Do you want to? Okay. Cool. Okay, so besides that, me complaining, we're going to see a similar pattern to deserialization in this implementation, because this is essentially deserialization, what we're doing. I'm following this, again, linear pattern of looking at the keys. This runtime string compare thing is, I think Louis was alluding to the fact that HANA equal will compare. Oh no, actually that's not relevant, because HANA equal on const char stars will compare the pointer, not the values. But runtime string compare here is actually a facility that will go over every character and compare them, probably using a fold expression. After seeing the deserialization example, this is kind of repetition, where we access the map, we get this meta info, we get a pointer out of the meta info, we get the type out of the meta info as well. I think there's a bug in the current implementation, again, of the CPP3K fork, where what I'd like to do is say decal type info : type, and for that to just work. It doesn't work. It really doesn't work for templated types. So unreflect member right now is this crazy thing that uses decal val and decal type, which if you're curious, I'll show you later. Because we're dealing with kind of simple primitives right now, we're going to do a lexical cast. That's why we need to get the type out, is because the interface for Boost lexical cast requires you to specify the type and use a member pointer to set that. Okay, so I wanted to see if this work I was doing, playing around with reflection, was any improvement at all on Boost program options, raise your hand if you've used Boost program options. Yeah, it's a very commonly used facility for this problem. Boost program options requires you to collect a variable map of options, and then after you parse it, parse argc and argv, you have to do an any cast to get your values out of the variable map. So the intuition is, not having taken a close look at the implementation at all, the intuition is maybe this kind of strongly typed approach is going to be better in some way. So as a back of the napkin benchmark, I went with binary size. Again, as we know from using like OFAST, the size of a binary is not correlated with its speed, but this is a graph that's not showing up. I'm so sorry, guys. Okay. Sorry, I would like to show this, so I'm just gonna run into yeah, this is terrible. Okay, yeah, so I also did a kind of a ridiculous benchmark, which is I generated a benchmark for up to 45 arguments. And it's very rare you're going to have 45 arguments to a program. I had a script that generated just like a struct with members. Yes, Alistair?
So when you say arguments, you mean essentially fields in the program options as opposed
Exactly.
to arguments on the command line.
Exactly. So I generated sources with a struct with 5 members with randomly selected names in increments of 5 up to 45. And I compiled them, I think at 03, and compared their binary sizes. And I varied it over such a large size simply because I wanted to see what the scaling factor looked like. And so luckily, the blue is the example that I made, and it is smaller. But it does seem to like grow faster in the small region, which I'm curious, but I haven't done a lot of analysis on this either. Because we're doing less work, we're ending up with a smaller binary. I do think that if I added some facilities to add help strings to this example, then this binary size would go up, because if we added like a really long help string describing our option, and that's stored at compile time. That's going to increase our binary size. But again, I wanted to show this as we're not just writing code for the hell of it. We're accomplishing something.
Just one small question. You have an
Yes.
asymptote around 25 arguments.
Ah, yes.
Did you find out why?
No, I didn't.
Very weird.
I was thinking that I was wondering that about that because program options might level out because they actually might have a limit on the number of arguments, or they might start dynamically allocating stuff. Yes, David?
Did you also do a graph on compilation speed?
No. Yeah.
Notice a difference, like just using it?
So because I'm generating a lot of benchmarks, yes, it does take a long time to compile, but not like hours. The benchmarks take like minutes. But yeah, I think that is an important point. So with reflection, my intuition is that the stuff that the implementation adds it's like a constant factor in the normal compilation times because it's just exposing stuff the compiler is already doing. But I haven't taken speed benchmarks. Yes, Zach?
So I think David Vandervoort was the one who brought this up in the last meeting. We were discussing this, and he said that he wants to do the object-oriented way of doing it instead of the type system-oriented way of doing it. Simply because he says even though you're reflecting things that already exist in the compiler, with an object you can just give that to someone. With a template instantiation that comes with the template-based one, you have to also instantiate a template just to communicate that same information. So he's afraid that it's something with like a ton of reflection-generated code for, let's say, a large amount of serialization or something. You get like hundreds of thousands of template instantiations you didn't want and very long compile times for your T's.
I was thinking that might be the reason for the asymptote. As in, at some point, the templates start overlapping and they are memoized.
Yeah.
So you don't get more templates.
Yeah, that could be.
How does the compiler memorize templates, instantiated types in that way?
From what I understand, if you have the template with the same kind of types, then it would just reuse the same instance.
Right. But if I have if for the reflexor implementation, for example, I have a different type for each member, then how will it know to memorize the...
You cannot memorize if they're different.
Right. So
it depends on whether the instantiations end up going into things that are the same underneath at some point.
Exactly.
I see.
So
Okay.
it depends
Okay.
on how different they are.
That's cool. Yep.
My guess for so this is data now, right? My guess for why the size is stagnating at some point, or rather why there's a gap, is there. It could be something else completely, but it could be that there's some better inlining going on for small sizes, and then at some point the optimizer starts giving up, and there's more code being generated, and you know once you kind of go past a point where okay the optimizer is not doing such a good job anymore, that's way more code being generated. Like you can't really tell the difference between one and n plus one. That is just like a theory like
Sure.
that, but I've seen stuff like that before.
Yes, Odin.
Did you also strip like RTTI and type info and stuff? Okay.
Not that much overhead.
Yeah, this is a really rigorous benchmark, as you can see.
If you're doing a lot of TMP stuff, it could make a large difference.
In binary size, yes. Yeah, absolutely. Are there more points on this discussion? Okay, cool. So kind of touched on a lot of these points. I did want to point out that for this example, for this problem of program options, what I'd really like is to have attributes. I'd like to have user-defined attributes and reflection on attributes. I think that it's another way to express information about our types that right now is a bit underserved in the language. But I think that if for example, someone decided to write a paper about user-defined attributes, it would need to mesh well with reflection, and that we would also want to add reflection on attributes. I also what I want to point out is, even though Alistair mentioned that we're going to have a really small number of members for in the kinds of types we deal with reflection, I'm concerned about this linear runtime string matching. I saw it and I was like, I don't like to pay runtime cost. So maybe as a thought experiment, we can see how we can make this better. So I decided to write a string hash so that we could compare the runtime strings in our examples in deserialization and in program options in constant time. So here's what would be really cool. What if we could implement a perfect hash from our set of strings to unique integers, then those unique integers to index into our type at compile time. So again, the runtime to compile time matching has been looked at before for implementing standard variant, but that is essentially looking at integers because the active type of a variant is represented as an integer. So how do we do this for strings? Well, if we take the result of a hash is going to be an integer, but it's not going to necessarily be a sequential integer that we can use as an index into that type. So we're going to need to do kind of 2 steps of hashing. And another thing is, I'd like to be able to compute this hash both at runtime and compile time. So then I can do things like detect if there's collisions to test it, or I can do things like determine the set of integers that we get from the hash and then map that to sequential integers. Because I might not necessarily get sequential integers out of my hash initially. So I did this. It's pretty fun. The really short and simple implementation, I'm calling it the simple string hash, is I look at my set of strings at compile time, and I get the max length from the total, the names of my members, essentially, if this is reflection, if this is for the reflection use case. But this isn't closely coupled to reflection. Then I define the hash function, and here I'm overloading operator paren to be fancy, to pretend like I'm a function. I add up the value of the keyword at index I, and I multiply that by its index offset by 1, and I add it up. And I can also do this at compile time. Here I'm actually using a custom string literal class, which is based heavily on, it's similar to the HANA implementation, sort of written as an exercise for myself, but it's a different way of writing this hash at compile time. And yes, Louis.
Can you go back one slide?
Yeah.
By just having a context for string length, which is not too hard to write, and I think it's the main context, but you could just throw context there and you wouldn't have to duplicate the definition. Does that make sense?
So for the parameter, because it takes const star keyword as a context per parameter, would that work? Like, oh yeah, because if you have context per lane, it takes it.
Well, so pretend that
Yeah.
operator brands can be fully context, but pretend.
Liza.
I think that can be done. So if that can be done, then at one point you have a context per string, and then you call your hash, and then what you get back is a context per hash because everything was context per all along. And that's what you then use like as an integral constant, maybe.
Cool.
I think that might work. You shouldn't have to. You shouldn't need to duplicate this definition.
Yeah, it is really bothering me that it's duplicated. Okay. So I just noticed that I'm sort of low on time, so I'm going to start rushing through this a bit since this is kind of side material. This is, we still need to map from the result of this hash because the way we wrote it is we're adding like ASCII values together, so we end up with actually very large numbers. It's really far from being from 0 to n. So we have another level of hashing from runtime integers to compile time integers. And this is here I use a recursive switch statement where I take seek in this example is the known set result of our string hash. And then I map that to sequential indices. So I wanted to benchmark this because I thought it was pretty cool. And I kind of generalized the stuff from the deserialize example into this thing, which is expressing the same thing in a very terse way. And it, without optimizations, it did really well. So the red is the, hopefully, it is the hashing example, and the blue is the linear example. And with optimizations, oh, the legend got cut off a bit in this slide, sorry. With optimizations, we can see that the linear example grows linearly from 0 to 50, and the red is actually, for a small number of arguments, there isn't a huge amount of difference. So this is, for anyone who's like, sorry, this is runtime speed. So I executed 1 million hashes and averaged that over 100 runs, and measured the total time. So you might say that for the case I'm really interested in is, doesn't exceed 10. It's going to be more like 5 for the members of my struct. I'm never going to get up to 50. That might not necessarily be true. There might be structs that have like hundreds of members. So I think for that case, it would be very important to consider implementing a string hash. Yes, Stephen?
So what if you wanted to implement your parameter thing for GCC?
Huh.
If you wanted to test something with a large number of members.
So I should say I've tested very little of the code in this presentation on GCC because the reflection examples are only in forks of Clang. However, the string hashing work that I've done, because there's no dependency on reflection, it should be fine. But whenever I could try to compile it with GCC, these are differences in how GCC and Clang have implemented 17, and I tend to abuse fault expressions and some other features. It actually doesn't compile with GCC right now in the current state of the code. So that's, but you were saying,
well, I was just saying, if you want to test,
GCC has a lot of arguments.
yeah.
Yeah. Okay, yeah. Yeah. Fair point. Also, I haven't. I think a cool use case for the program options example is with nested arguments. So if you could, yeah. Anyway, so imagine having like -- something dot something, and then having that deserialize into a nested member of a struct. But going back to string hashing, okay, you might ask, like, this is like barely even relevant to reflection. I don't disagree. There's also a lot of implementation caveats. So actually, in this use case, you'd want to have a hash from 0 to n characters for all strings, because imagine if your user is typing in program options at the command line and makes a typo. Well, that typo string is not in your string hash set, which I illustrated. So you actually want to be able to handle all strings. And if you want to handle all strings from 0 to n, that's a really, really big number, and you're going to actually, yes?
So have you considered instead of doing a hash doing something like building a DFA?
Yeah, I haven't done it yet. So the suggestion was build a DFA instead of a hash. I think the principle of this is, in order to make metaprogramming more practical, we need to think about ways to map efficiently from runtime to compile time, not just from integers, but maybe more complex data structures, and to push down that conversion to logarithmic or constant time. And I think that opens up a lot of possibilities for how this discipline can be more useful. And reflection also makes metaprogramming, I think, more useful and brings it to the forefront of tools in a programmer's toolbox. Okay, so this is something that we were discussing already, and a lot of that conversation probably wasn't captured by the camera, so I'll kind of reiterate. With type-based metaprogramming, so if you're instantiating a lot of types, if you have values that you represent as types and then you instantiate them, that could hurt your binary size or your compilation speeds. If you're crazy like Odin and you implement continuations using declarations, you could actually have compile times that are really fast. But I think that most people agree that the API that they prefer is something more with value semantics. And the point that that came up in our earlier conversation was that David has said that with value semantics, you're not instantiating types, you're dealing with context per values, and that is actually cheaper. So that's another benefit besides the kind of the saving human time that a value semantics metaprogramming paradigm brings. I apologize for not presenting you guys benchmarks, but I also kind of felt that these implementations do not represent the final product. One thing that I learned through doing this presentation is the designs are still evolving, and also there's a lot of quality of implementation issues for the compiler. And I think a presentation that presented a lot of compile speed benchmarks should be on a more polished product. Does that make sense? Okay, so we're going to shift gears. We looked a lot at real code that does compile. I'm going to show the link to my examples at the end of the presentation. And we're going to look further into the future. One thing that isn't really hammered down yet, but is being worked on is function reflection. There is a limited facility for this in the CPP3K implementation, which is, it has some limited facilities, which are still really useful. So if you've ever written a really cryptic function to get the arity of an invocable or a callable or whatever we're calling it these days, or maybe just a function object, what if you could just do reflect on my function and get the size of the parameters, and that's the arity. It's great. And then this is very fictional and doesn't exist yet. But what if we could reflect on overloads so that given the name of a function, we got a sequence representing, that was a representation of all the function, the overload set of that function. But, you know, what if we could hammer down the overload ordering rules such that the ordering of the overloads in the sequence was actually the precedence of overloads? Wouldn't that be cool? I'm not enough of a language lawyer to design this, I think, or really to make decisions about it. But I think it. Sorry, what?
It's not a total order. So we can sort it.
It depends on the argument type.
Yeah, exactly. It would depend on the call site, and it would also there's a lot of issues with the syntax to reflect on the name of a function, because a lot of people want to be able to reflect on lambdas. So we would also have to. I think we want to be able to reflect on a broader set than just member functions. We want to reflect on lambdas and function objects, like things that can be called. And this starts to get very complicated quickly. Yeah. I also think that before we go too far with one reflection design, we should address kind of an elephant in the room, which is that everything that's been proposed and implemented so far is just introspection. And I'm going to have some redundant slides with several other presentations that either will be or have already been presented at this conference, but hopefully that will serve as a data point that this is an important issue. So I want to be able to change identifiers at compile time. And I want to be able to do this because once you've reflected on an object, you can do cool things with data layout, but there are all these facilities that would make programming easier that we can only really unlock if we can kind of implement traits or play around more, like make new classes based on the, now that we've unlocked reflection information, we want to use that as inputs to another kind of set of templates that we can write. So this is more completely fictional syntax that is not implemented yet. It's sometimes, I think in the Reflexper papers, it's, you know, initially been referred to as ID Reflexper. Peter Bindel in his talk called it Reify. And I'm going to give it another name because I feel that ID Reflexper is too closely tied to reflection. ID Decal is like identifier declaration.
But it's missing the expert suffix.
Do you think it should be ID expert?
Every new keyword should have expert.
Because it's so easy to pronounce.
Yeah. So we should end up with expert.
Right. Yeah. So this is why I showed the D example in the beginning, because C++ currently has nothing that achieves what I'm about to show. So imagine we could use ID Decal, and given the data members resulting from reflection expression, what if you could actually pack expand that in a member declaration? And this is some more fictional syntax. And what if that pack expansion could also be in lockstep with getting the member types? So we could declare the member types, and then we could declare the names of those members in order. So the result of this in my fictional land is A of person is going to have all of the same members as person. And this is a total toy example because it essentially achieves like hack inheritance. You know, how is this any different? Or, you know, it feels like it's actually worse than inheritance because I haven't recorded that there's a relationship between these structs. Well, I actually think this is cooler than inheritance because you could filter on a predicate about those data members. And rather than inheriting from something, you could have a more expressive relationship between them. So for example, you could say, I want to get all of the pod members of T for some reason. Maybe that defines something like, that defines that this is serializable, or that defines that I can do a safe operation with these. As has come up frequently, you can implement mocking with this. So you would need some kind of map from the requirements of your mocking interface, and you could declare a set of member functions with the same name and the same signature. And this is where the syntax starts, I think, really falling on its head, because there's so many things we're trying to express here that are impossible in the language right now. Trying to have a pack expend in a member declaration, trying to have this like generic args. This is the kind of stuff that we achieve with macros today frequently, but we're introducing tons of new language constructs in this slide, and it's totally a mess. So there's some ideas in another paper, which was written by David and Louis. It's called Exploring the Design Space of Metaprogramming and Reflection. And that makes the point that we can't move forward with reflection unless we have better facilities for metaprogramming in the library, for dealing with compile time sequences, for dealing with the issue of declaring an identifier at compile time rather than doing some hack with the preprocessor. So this is maybe a cleaned up version, but it's still a bit odd because we have a const expr4 in a struct declaration. I don't know if that's a part of your proposal, but being able to have a const expr block and a for within the like in a struct definition context.
Yeah.
Oh, cool.
Well, that's one of the things we explored. So I'm going to say.
Yeah. So yeah, a huge boon, I think something that would also enable us to stop abusing fold expressions is a heterogeneous context-aware for loop. And the way that could be used with ID decal is this mocking example where we want to iterate over all the functions. Another weird part of kind of what would be cool to see, though, is having this kind of function declaration using the result of fictional ID decal. It probably a compiler writer would look at the number of new constructs on the slide and be like, we have a lot of work to do until this is possible. Another thing that probably a lot of people at this conference have already seen already, but I think is in the future of the language, is the idea of implementing virtual traits. And this is a library we wrote called Dino that introduces a new way of dealing with runtime polymorphism. So it requires some boilerplate in order to implement an interface, which is kind of delegated to some to the polymorphic storage. So if you look on GitHub, you can find an intro example to this library. We're running out of time. I'm not going to totally explain it, but we can take a little bit of boilerplate out of this by saying define the interface, then define this concept map template, and in that we do this ID decal thing where we delegate to the underlying polymorphic storage instead of in the library as it is right now. You have to define drawable essentially twice and define the signature twice. Okay, and there's other ways, many other ways to use the ability to define a parameterized identifier, member identifier or function identifier at compile time to implement customization points. Go to Michał Dominiak's talk if you're wondering about how this would work.
But we learned that there are macros there. In the
Don't be afraid of macros. Yeah. So as I've said, there's a lot of caveats with this design. This is really idealistic design. I'm showing the design that I, as not even a library implementer, a user of the language, would like to see. That would open up metaprogramming a lot to people and enable us to write a lot of useful facilities for reasoning about types and having different relationships between types. But there's a lot of questions. Do we want to be as flexible as D with hygienic macros, where we can insert arbitrary context-aware strings into something and have that be, a valid identifier, or even just write arbitrary code and have that be compiled into our translation unit? Or do we want to have a more structured interface with more rules? Do we want to add more rules to this language that, there's maybe 2 people in the world who understand every rule of C++ in every corner case, right? Clearly, there's something missing here. And I'm not going to talk too much about it because I'm not an expert. And the vision for this going forward, the person who's really championing it has specifically asked us not to talk too much about it. But I'm just going to say, I'm going to let this guy continue the conversation. But unfortunately, you're going to have to wait a few more months to see what the next installment of this journey is and what the answer to my questions are. I'd also like to thank a lot of people who have helped me with putting this presentation together, helping me learn, and also hopefully creating a body of work that we can all continue on to have a more powerful and expressive language. And if you want to see all of the code, including some code that didn't make it into this presentation, and the source for this presentation, you can go here. Thank you, guys. Got like 10 minutes for questions, right? Michael.
Yeah, not really a question, but more of a comment. With these types that you're generating, I think what I would like to see is that you can specify an optional target of the file, so that they can actually see the types that you're generating. Because if you're doing a lot of filtering and stuff, generating new types out of them, I mean, how the hell are you going to know what's in there unless you write code to see what's in them?
But if you can reflect on whatever's in there.
But I need to write code, or if you have an IDE, right, that you want to type. So, I mean, not to actually use. I mean, every time we build a program, it should be generated, but not kind of .o file, but it's an intermediate kind of thing.
So you want to be able to reflect on the intermediary types generated by the compiler by Reflexper or by metaprogramming,
I mean, the ones that you're
like
creating,
template instantiations.
is your class creations. So I want to be able to see the outputs of those. I want to see those types that they actually look like.
Louis is really excited to answer this. I don't know.
It's pretty easy for the compiler to just give you like a meta colloquially debug thing that you throw on your struct, and it just prints out the results. And that's one thing you may or may not be implemented by a standard, but it's very easy to.
You could also implement it in a library because it's basically a fixed thing based on Reflexper.
No, you really like to add like an actual just bunch of C++ code. Basically, what happens when you say Clang dash E, right, for just running out the processor.
Well, that would be like dump AST, I think.
Something like that, right? Yeah. So it is possible. Just fuse the C++ code that it gives you, and
So there's a couple, to summarize, there's things like Clang dump AST, get debug name of my struct. There's macros for like dash dash underscore file, also for introspection for something. But also one funny trick is sometimes if you have like a very complicated type and you're instantiating this type and it's not clear like what the name and all the arguments are at the call site, if you make an intentional typo, sometimes it will like expand it out. I think Heel taught me this. I don't know. Sorry, questions? There was some questions over here. No. Yes.
I was just commenting on the previous thing where I think the generative types, they should be debuggable. So I think it makes sense what the first person said is just write them out to a file and then I can step through the file normally and like it's much more easy to work with that.
Yeah, I mean that's not a language issue, right? That's a tools issue.
No, I have to be able to write a file from the language, right? So that I can then step to that file later.
So this whatever proposal ends up being standardized just needs to say, by the way, there needs to be a facility called like the meta debug or whatever, which accepts that kind of expression and gives you an implementation defined string, which is meant to be useful, right? So you standardize that, and then every compiler is just going to give you the code that is being generated. Okay. I think that's sufficient.
So instead of static assert, something like static printf.
Whatever, yeah.
Static printf.
This is just for debugging, so that's totally possible. I just
Well,
want to say with regard to this, like the standardization committee is open to papers for such ideas.
Yeah. One thing about
yes, this is the equivalent of Patch's book.
one thing about reflection actually that might be relevant here is right now you can only reflect on instantiated templates types. Like you can't reflect on a template. I think it would be cool to have some interface that's like walk the layers of nested templates of a type, or like and walk across the parameters for like a template definition. Some people are making faces that are like, that sounds terrible.
Specializations.
Yeah.
Like all that happens at the point where you are manipulating it.
Okay. One can dream.
Yeah, templates aren't really a thing. They are meta things that generate things.
So you have to have like.
But they have to get parsed at some point, right?
Rather than a point of instantiation, you have like a point of parse, and then everything before that you see, and everything after that you don't.
Yeah.
Maybe you need like a meta reflex for.
Great idea.
Well, wouldn't that be expert?
Yes, David.
Reflex. So like with regards to like our approach, is we're trying to
we know we can do, this we know how to do, get that moving through, and then we'll get more usage experience, we'll see what's necessary. Because there's a lot of things like, oh, it'd be cool to reflect on templates, it would be cool to reflect on this, where the question is really, really open, and if we try to put that in a proposal, it might kill the whole thing. So that's why we have this strategy of putting in the low-hanging fruit first, and then we'll see where it goes from there.
Alistair?
Just to clarify that I heard correctly, we can reflect on an instantiated template,
Correct.
but we cannot reflect on an uninstantiated template.
Correct.
You can reflect a type essentially, right? And an uninstantiated template is like a type. So. Yeah.
Any more questions? Comments? No?
I want this.
Yeah. I mean, who in this room doesn't think reflection is a good idea?
Why are you in this room?
Why are you writing papers about that?
Alistair.
I'll say when I came into the room, I wasn't sure it was a good idea, and you sold me, so thank you.
Wow, thank you. Yes.
I think that introspection is a very good idea, but code-generation is a very bad idea.
So,
We drastically need good generation, code generation.
Because the idea that it's not a problem of the language, it's a problem of tools. It leads to know tools, to all tools, to enormous, to big calculation times, and so on. To all the problems why people don't use C++ and use Java, for example.
so the comment is introspection is a good idea. Code generation is not a good idea. Code generation is a tooling problem, and we would simply it seems like the main argument is compilation times.
So I have like a counter argument, like every tool you have to use is an additional build step for your project, and this is a problem that has not yet been solved in a sensible way cross-platform way. Like CMake gets close, but not all the way there. So it's very hard to integrate some tools, and like some people are have a stance of I'm not going to use this because it requires me to use external tools.
Odin, yeah.
Yeah, two comments on that. I think as soon as you're using an external code generator, the granularity of your interface with that code generator is coarser. And also diffs are terrible, but whatever. The problem of compilation time is not always metaprogramming, but very often metaprogramming. And I think Louis' proposal on metaprogramming will be much faster, as well as I understand the compiler, which is not super. But you know, the work that I've done, I've seen compile times go down considerably, like sometimes orders of magnitude versus boost MPL. And the reason it does that is because I'm creating less types that nobody cares about, right? Like a type that's just there to be able to compute the next type. And if you take, and the other thing I'm doing with fast tracking is basically lowering the amount that I have to string things along because I'm going to work on them later and still need them, right? You know, passing a parameter from one alias to the next alias to the next alias, and somewhere way down that fold, I'm going to use it, right? Both of those things that I've been trying very hard to reduce and getting better compile times out of it are not a problem at all with Louis', you know, const expert type as a value metaprogramming. You don't have to string things along, and you're not creating any types that you won't end up needing. So I predict, I don't know, maybe, you know, maybe I'm wrong, but it's going to be at least another order of magnitude faster for you know, than my stuff, which is already arguably 2 orders of magnitude faster than what people are typically using, because it's typically boost MPL at this point. So the template metaprogramming portion of compile time is going to go away.
I just want to point out that I don't think it's productive to talk about the increased compilation speeds of a feature which hasn't been designed or implemented at all.
Well, it doesn't need any allocation within the compiler to compute most things, and that I think is you can you can predict that that's going to be faster then.
So just one quick comment, I guess, on to answer your concerns. One thing that is easily done, well, more easily done if you use code generation inside the compiler, inside the language, is that you can extract, information from your program and then do computation on it and then generate a code based on that. If you're using an external tool, the external tool, to do its job properly, may have to implement essentially the full C++ parser key. So it's useful to basically have you're already compiling, so now you have the AST representation, you transform it, and then, you do something with it right away. There's some convenience to that, I guess.
There's another benefit, which is the thing that Visual Studio had as a problem in the past. If you have different parsers for a certain language, they are going to be subtly incompatible with each other. You had a problem in the past that your highlighting would say one thing, IntelliSense would say a second thing, and the compiler said a third.
Well,
they had three front ends that were not compatible.
the problem with having multiple parsers, though, is if we had good introspection, I think that what am I trying to say? We can have multiple C++ parsers, and then we can generate introspection code from that, and then that introspection code will differ. That's bad. So let's standardize introspection. I think it sounds like actually we're all agreeing on that that's a good thing. But then there's should we be able to generate C++ code from C++, essentially? So should we be able to, within my compilation unit, after I've reflected on some types with these like meta template utilities, be able to create a new type based on that with new identifiers based on the identifiers of another header? So I think it's a good thing. I think it enables people, and I think I'm just repeating essentially what Louis said, which is that you've already gathered all this AST information that in a standard way, and you can also probably exploit the fact that you're already compiling this this program, and you have all this information to do that in more quickly than an external tool would. Jeff.
I have another example that's a real world one. Many projects reflect C++ and other languages, so inevitably you use Swig.
Yeah, I was thinking about that today.
Please.
Yeah.
Once and for all.
FFI.
Code, yeah.
Yeah.
So that's generating a C interface, right?
Uh-huh.
Typically, because all of the other languages can interface with C. So really, if you think about it, even if I have an object-oriented thing, I need to generate like functions, a pure functional interface. Yeah.
Yes.
Just another comment on the same topic is, so we already have two ways of generating code. One is macros, the other is templates. And most C++ programmers hate macros, and most C++ programmers hate templates. So if you write a third way of generating code, let's just make sure nobody hates it. Or like, let's make sure fewer people hate it than the people who hate templates and the people who hate macros. Should just be less hated, please.
This one is going to be designed. All the other ones are macros are just macros, but like templates are just accidental, right? So this one we're
Templates are accidental.
Designed to be coded. Right.
Well, a limited form.
They weren't initially designed to be Turing complete.
Yeah. Yes.
Which is why we have all this mess.
They were designed to be what C# has as a generic, but they accidentally do a bit more.
A little tiny.
Sure, please.
Yes.
I'd like to ask a question. Who here is familiar with list macros? Okay, so maybe there would be list macros don't operate in terms of text manipulation like C++ or C macros. They work in terms of AST. When list compiles a function, if it sees a macro, it executes that function immediately, and it gets an AST, which is the parameter or parameters of the macros, and then it returns a new AST, which is substituted to the macro call. So maybe that's an idea to explore for code generation.
That's definitely an idea. This is part of, like, we present 3 or 4 different ways of doing code gen in the paper that was cited before. One of them is, we say it's a programmatic API to code generation, which is, I think, what is the closest to what you're saying. One problem I see with that is that Lisp AST is very simple. C++ AST is not. So if you're going to have to manipulate this AST, it becomes very complex very quickly, and you have to know about things which you don't care about, such as statements, expressions, declarations, and you have to know all these entities to manipulate this AST properly. That's what I've seen so far.
So have you used in this macros the template facility?
No, I have not used this method.
So in this macros, you could start building the AST by consing and all that crap. But they have something else which is you have a way of quoting form, okay, let's say data structure, where most of what you're going to write inside it is constant, but for some parts of it you can insert variables. So it allows you to build a very complex AST by simply writing it and incorporating substituted parts. So maybe that could be interesting as well. I see very clearly how a macro like min or max could be written that way.
So the point is, first of all, it's past the allotted time for this session, so if you need to go, then feel free. But I'm going to continue for like 5 minutes talking. The idea to have an interface similar to Lisp macros, Louis points out C++ is way more complicated than Lisp. So having an interface to being able to change the AST would be way harder to implement. I was actually thinking about this because if we could generate code at compile time, like one safer way to do that is to have an API that's like similar to Clang AST matchers, if you've ever used that, but it essentially enumerates the constructs of the language, and that would enable you to declare something. And that's what some other languages that have reflection have stuff like this, where they have like an interface that basically mimics, or it's almost like a mirror of the standard of the language design. But it is adding more complication. I guess it would be adding some library complication. Maybe we could have a language level mechanism for this, and then the API would wrap it in a kind of like type safe way. And that would be more hygienic than having macros. Yeah. Okay, thank you guys.